In this chapter, we'll be talking a lot about exponential and logarithmic functions. We'll start with their basic properties, such as domain, range, what their graphs look like, and all that good stuff. And then we'll get into many of their applications, such as finance and in science. To start off with exponential functions, basically we often define an exponential function to be in the form of f of x equal to a to the x, where we often refer to as a as the base of the exponential function and x as the exponent. So, for example, f of x is equal to 4x would be an exponential function. We might say base 4. And one key thing, since we've talked quite a bit about polynomial functions in the previous chapters, I wanted to emphasize what is the key difference between an exponential function and a polynomial function. A polynomial function is consisting of power functions such as x squared, x cubed, basically where x is raised to a particular power, often written as x to the k, where k is a constant. And the key difference here, it's obviously easy to interchange these because they're both exponential expressions, but the difference is that x is in the exponent as opposed to being in the base. In polynomials, x is in the bottom, and the power is consistent. In an exponential function, the exponent is what is changing, and the base is a constant. And that being said, it causes quite a few differences between that and polynomial functions. There are some similarities, but they're their own category of functions, and also quite important. Probably a lot more important actually than polynomials to most sciences. Anyways, let's start off by just looking at an example and creating a graph and using that to figure out and think about what might the domain and range be for an exponential function. But for example, let's just try plugging in integers to begin with. Like, let's say we had 4 to the x power. We want to know, well, what happens if I plug in 0? Or again, that would be also asking, what is the y-intercept? Well, if I plug in 0 into f of 0 would be 4 raised to the 0 power. And if you recall from algebra, anything to the 0 power always makes 1. And actually, in the next video, maybe I'll review some of the basic properties of exponentials, because this is one of those weird things where it doesn't necessarily make sense, like why is it 1, if you don't really think a lot about what exponential notation means. And I do want to get to that. But for now, let's just focus on finishing evaluating and looking at the graph and stuff, and we'll come back to that in the next video. But in this case, continuing, 4 to the first power is equal to 4. 4 to the second power is equal to 4 squared. Remember, that is not 8. One easy thing to fall into is thinking about exponential notation always means multiply, but it doesn't mean directly multiply. It always means that we're going to have that many factors of a number. So 4 squared would be 4 times 4, or 16. And that's actually a simple reason as to, well, why is 4 to the 0 not 0? It's because we're not multiplying 4 times 0. That's not what it means. It means we have no factors of 4. And if you're talking about a factorization, any polynomial with no factors would always have to include 1. I'll talk about more about that in another video. But graphing some of these points, the y-intercept would be at 1. If I plug in 1, I would get 4. And if I plug in 2, I would get 16. And also, if I wanted to know what would keep going, like say I was thinking about, well, what's the end behavior? What happens as x approaches infinity here? Like looking at, well, what about if I were to plug in 3? Well, 4 to the third power, just like with polynomials, when you start plugging in larger and larger values for x, what will happen is, of course, since it's exponential, it will get larger at literally an exponential rate. And we refer to this as exponential growth. Basically, it grows super, super rapidly. And of course, 4 times 4 is 16 times another 4 would be 64. And if I'm trying to graph, of course, that would be, way up here, way too high for me to graph. But basically, the graph will, the end behavior will approach infinity. As x approaches infinity, f of x will also approach infinity. But anyways, also, if we wanted to, we can actually graph more points in here, because these points give us sort of an idea of what this looks like. And if I didn't know any better, I might think this looks sort of like a parabola. But actually, what I wanted to look at is what happens if we plug in, say, 1/2 or 3/2, and wanted to graph, like, well, what is 4 to the 1/2 power? And another thing, a review from intermediate algebra is remember that a fractional exponent always means is equivalent to the square root of a number. So the square root of 4 would give us 2, which would be right here. So if I plug in 1/2, I would get 2. And if you're a little bit rusty on your exponents, like fractions and negatives and zeros and stuff, you can always use a calculator if you are, unsure of what will happen. And another one, actually, I'll go ahead and add another value to my table here, is what about 3/2, just to kind of make my graph a little bit, as good as possible. If I was to do 4 to the 3/2 power, that would be equal to the square root of 4 cubed, which would just be 2 cubed. And again, these are all properties from algebra. Basically, if I have I'll go ahead and write the property on the screen, just, if this is one you've forgotten. This would always be equivalent to the nth root of a raised to the n power. And I'll write it like this. And actually, there's various different ways you can do it. Oops, my screen wasn't on my screen there. But basically, that's if you're wondering what does a fractional exponent mean, what is that's another property from algebra. And again, I don't want to explain that at this point in time. But this would leave me with 8 in this particular case, because the square root of 4 is 2 to the 3rd power would be 8. But basically, the thing I wanted you to see here is there is a pattern within an exponential function. It's obviously not linear, but what happens is it grows at a very exponential rate. There is a smooth curvature to the exponential function, and it's sort of similar to a parabola. It's not a parabola, though. It's its own unique graphical growth trend. Also, if I were to plug in negatives into this here, this would leave me with 4 to the -1. Remember that raising an exponential, raising 4 to a power of a negative, that never actually makes it negative, because again, we're never directly multiplying the numbers. A positive times a negative is always a negative, but a negative exponent has a different meaning. Negative exponent always means reciprocal, or in this case, it would give me 1/4. And 4 to the -2 would be 1 over 4 squared, which would be 1 over 16. But basically, all of those trending patterns, and if I was to do 4 to the -1/2 power, that would be equal to 1 over the square root of 4, because again, the negative exponent means reciprocal, means divide instead. And a fraction would mean take that particular nth root of the number, or it would leave me with 1/2. And again, if this is, I'm not expecting you to necessarily be able to do all this math in your head, because these are all just, I chose this example because each one of these evaluates relatively simply. But you could always use a calculator. If you're not really sure, that's kind of another point, is a calculator can easily determine any number raised to any other power. So there's not really mystery in a modern perspective when it comes to evaluating these things. But there is some sense behind them, and you can evaluate certain exponents like this without a calculator. Anyways, continuing with my graph, I would have 4 to the -1 would be 1/4. So if this is 1, 1/4 would be, quite a bit smaller. So, it'd be real small. Also, you might be noticing the graph looks a little bit strange here. But this graph is, I've changed the domain and range from, a more standard -10 window, because with exponential functions, we often use what's called an exponential graph, or a logarithmic graph, to graph these sorts of things, and they just look a little bit different. But the point is to sort of emphasize the values that we know and we're sure about. But basically, the thing I wanted you to notice is that as x goes to -infinity, when I plug in -1, I get 1/4. When I plug in -2, I get 1/16. If I were to plug in -3, I would get the reciprocal of 4 cubed, which would be 1 over 64. But basically, as I move to the left, it's getting smaller and smaller and smaller. But it's never going negative. It's actually approaching 0. And what this means is that exponential functions have a horizontal asymptote. And a baseline exponential function without any other transformations applied to it will always have an asymptote actually just at the x-axis, but the equation y is equal to 0. is the equation of a horizontal asymptote. It does not have a vertical asymptote though, because there is no division, there's no undefined values. And this is kind of another thing going back to the domain and range. The domain is actually all real numbers for exponential functions, because it is a little bit weird when I'm taking 4 to the x power and trying to plug into it. Plugging in negatives or fractions or weird values is a little bit strange, but my point is you can do it. You can always plug in fractions, you can plug in negatives, you can plug in 0. All values of x are defined. Even irrational values, say you were wondering about this one that I skipped, what is 4 to the root 3? This is one that is way too difficult to do without a calculator, at least with where we're at. But you can always figure it out. And that's my point in doing this. I could always approximate the value. It's not exact, but often it will result in another irrational value, approximately 11.04. And also it will fit on this general arc. It's not really an arc, but the general shape of an exponential function, because the square root of 3 is approximately 1.7. And if I go to that point on the curve, notice, it falls in line with this shape. And basically, this is the general shape of exponential and logarithmic functions. They have this very unique curve, again, which we often refer to as exponential. And the thing about the range that, again, we can notice from the graph, and also just by looking at all of the output values on our table here, is that the range values are never negative. And this is another property of exponential functions in general, is that the ranges are, again, unless they've been transformed for just a baseline exponential, is always 0 to infinity, because it will never produce negatives, and also it can never make 0. Like if I was to look at the equation 4 to the x equals 0 and I wanted to know, is this possible? This is actually an impossible problem. There is no solution to such an equation, because exponential functions have no x-intercepts unless, again, if you can imagine taking that graph and moving it downward, and if you move this graph downward, it would actually have an x-intercept and it could be 0. But in its base form, when you just have this sort of situation, there is no way of solving this. There is no potential solution. And that just means 0 is not within the range, and same with negatives. And actually, it's very similar to quadratics and polynomials, because technically, let's say I was to try to solve an equation 4 to the x is equal to -1. These sorts of equations actually do have solutions, much like this, x squared, equal to -4. It's a very similar phenomena, but when we try to solve things like this, we end up with imaginary answers. And the same thing will happen with more complex solutions. But all of that being said, really the range is 0 to infinity. It can't be negative either. And actually, technically, it can be if we expand the complex number system, but that is out of the, again, getting too far ahead in the history of math and in the scheme of things. But anyways, in general, what I suggest remembering and taking away from all this is that exponential functions, you can plug in anything into them. They always will have this sort of general curvature to them, general range, and asymptotes, and they all have very similar properties. Now, obviously, if you change the base and you tweak it, it will obviously affect the shape and so forth. And say you were to add 1 to it or subtract 3, and transform the graph, it could actually have intercepts and so forth as well. But it's important to understand the baseline. In the next video, I'll talk a little bit more about, well, why raising 4 to, why when we raise a number to a 1/2 power or a negative number, why does it work that way? Why does this become a square root? Why does it become negative? That's something we often are taught in algebra, but we don't really conceptualize. And I think it's kind of interesting.